Welcome to the session of finite element method. In this session, I will going to discuss about terminology used in finite element methods, my dear students. So, first of all, what is meant by element? What is meant by element, my dear students? Consider it is a domain or a structure. Now, this domain or a structure divided into small pieces. So this is a domain or structure. A small piece from the domain. This is a small piece. So from the domain, okay, a small piece from the domain with known characteristics. Now this domain is divided into small pieces, that is small rectangles, so that we know the characteristics of rectangle, that is with the known characteristics. Okay, a small piece from the domain with known characteristics, that is called as an element. So here is, I will write down here, a small piece from the domain or structure with known characteristics, so that piece is called an element. All of you clear, my dear students? So the next one is nodes. What are the nodes, my dear students? What is meant by nodes? Now, similar fashion, consider it is a domain or a structure. It is a domain or a structure. Now this domain is divided into small pieces. The joining points for this, it is a one element, it is another element. It is a joining point for this element and this element. It is a joining point. So for this element, it is a joining point. For this element, it is a joining point of small pieces, that is elements, that are called nodes. So here is joining points of small pieces, that is elements, are called nodes. Or there is another fashion, the nodes are connected points. It is a connected point. For this element, it is a connected point. The nodes are the connected points. Or the nodes are those points where the elements are connected with each other. All of you clear, my dear students? The points where the elements are connected to each other, that are nodes here. Suppose here it is a point. So this element and this element connected here. It is element. This is a connected point for this element. So for example, see, I am assuming it is a element number 1, it is a element number 2. It is a connected point for this element number 1 and element number 2. So here is 2, second element and third element. It is a connected point, second element and third element. So here is, the nodes are those points where the elements are connected with each other. Where the elements are connected with each other. where the elements are connected with each other. So that points are called as nodes, my dear students. All of it clear? So next one, types of nodes. Types of nodes, my dear students. What are the different types of nodes? So there are two types of nodes, my dear students. There are two types of nodes. There are two types of nodes. So number one is external nodes. Number two is internal nodes, my dear students. Internal nodes. First of all, we will discuss about external nodes. What are the external nodes? External nodes, my dear students. The nodes which are present over the boundary surface of the element. Suppose it is a element, my dear student, my hand is element. So whatever the nodes are present over the boundary surface of the element, that nodes are called as external nodes. So these nodes, for example, it is element 1, it is another element. So these nodes are common to other element also, other elements also, my dear students. For example, consider here, suppose it is a triangular element. Again, there is another one is a rectangular element, my dear students. So whatever the nodes are present over the boundary surface of the elements, these are all the nodes. Here is 1, 2, 3, 4, 5, 6, 7, 8, 9. These nodes are present over the boundary surface of the element. That nodes are called as external nodes, my dear students. Again, consider for rectangular element. Here is node 1. Here is node 2. Here is node 3. Here is node 4. Here is 5. Here is 6. Here is 7. Here is 8. Here is 9. Here is 10. Here 11. Here is 12. So the nodes which are present over the boundary surface of the element, that nodes are called as external nodes. The nodes which are present over the boundary surface of the element, over the boundary surface of the elements, that the nodes are called external nodes, my dear students. External nodes. So these nodes are common to other elements. These nodes are common to other elements. All of it clear, my dear students? For example, consider it, there is a structure is like this. For example, it is a structure. Now I am dividing this structure into small pieces. Now these are all the external nodes, my dear students. So these are all the external nodes. These nodes are common to this element also. These nodes are common to this element also. So that is about these nodes are common to other elements. All of it clear? Next one, coming to internal nodes. Internal nodes. Okay, consider similarly, same example, consider a triangular element and a rectangular element. Whatever the nodes are present inside the element, here is one node, here is another node, here is another node, here is another node, here is one node, here is another node, here is another node, here is another node, here is another node. whatever the nodes that are present inside the element, that nodes are called as internal nodes, my dear students. Okay, these nodes are belongs to only this element. These nodes are not common to other elements, my dear students. Okay, these nodes are specific to particular element and are not common to other elements, my dear students. So see, the nodes which are present inside the element, that nodes are called internal nodes, my dear students. Internal nodes. So the nodes, whatever the nodes that are present inside the element, for example, my hand is a element. Whatever the nodes are present inside the element, that nodes are called as internal nodes. These nodes are specific to particular element. These nodes are specific to particular element, my dear students, and are not common to other elements. And are not common to other elements. All of you clear? So here is node 1, 2, 3, 4. Here is 1, 2, 3, 4, 5. All these nodes are internal nodes, my dear students. All of you clear? So next coming to, there are two types of external nodes, my dear students. So again, the external nodes are divided into two types. External nodes are two types, my dear students. Under that, the first one is A, primary external node. Primary external nodes. Second one is secondary external nodes, my dear students. So first of all, what is meant by primary external nodes, my dear students? Primary external nodes. So see, my dear students, suppose I am consider a triangular element and rectangular element. So whatever the nodes are present at the corners of the element, whatever the nodes are present at the corners of the elements, that nodes are called as the primary external nodes, my dear students. Suppose this is 1, here is 2, here is 3, here is 1, here is 2, here is 3, here is 4. 1, 2, 3 are primary external nodes. Primary external nodes here. Now in this case, 1, 2, 3, 4 are primary external nodes. Okay. Now the nodes which are present at the corners of the elements, that nodes are called primary primary external nodes, my dear students. All of it clear, my dear students? Next one, coming to secondary external nodes. Secondary external nodes. Secondary external nodes, my dear students, I am consider same example. Now it is a triangular element, my dear students. It is a triangular element. It is a rectangular element. Now, what here is a primary external nodes. This 1, 2, 3. These are the primary external nodes. 4, 5, 6, 7, 8, 9. Similarly, here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So here is whatever the nodes present between the primary external nodes, that nodes are called as a secondary external nodes, my dear students. Now 1 and 2 is a primary external nodes, 4 and 5 is a secondary external nodes. So 1 and 3 is a primary external nodes, 9 and 8 are secondary external nodes, my dear students. 2 and 3 is a primary external nodes, 6 and 7 are secondary external nodes, my dear students. So here is, so I will write here 1 comma 2 comma 3 comma 1 comma 2 comma 3, these are primary external nodes. Primary external nodes. So here is 4, 5, 6, 7, 8, 9. That are secondary external nodes, my dear students. Secondary external nodes. Now I will write here the nodes which are present between the primary external nodes, that nodes are called secondary external nodes, my dear students. All of it clear? So in this case 6, 5, 6, 7, 8, 9, 10, 11, 12. These are all secondary external nodes. 1, 2, 3, 4 are primary external nodes. Now both primary and secondary external nodes are common to other elements. So here is, these are present over the boundary surface. So it is common to other elements. Suppose there is another element is joined here, it is a common to other elements. Okay. So both primary and secondary external nodes are common to other elements. Common to other elements, my dear students. Next one. Here is, what is meant by primary field variable? Primary field variable, that is, it is also called as nodal field variable. Nodal field variable. It is also called as nodal field variable, my dear students. So all of you see, my dear students, it is a bar element or line element. Here is a node 1, here is a node 2. This is element 1. So at this point I am applying force here. It is a P1 at this node 1. At node 2 force is a P2. Okay. So because of the force, the node 1 is displaced by U1. Node 2 is displaced by U2, like this. Node 2 is displaced by U2, my dear students. Whatever the parameter which varies immediately with the application of the load in the domain, that parameter is called as primary field variable or nodal field variable, my dear students. So because of the load, this node 1 is displaced by U1, the node 2 is displaced by U2. Which parameter is varied here? The nodes are displaced. So that here is a displacement is a primary field variable. The parameter which varies immediately with the application of the load in the domain, that parameter is called as a primary field variable, my dear students. Here is a displacement is a primary field variable here, because node 1 is displaced by U1, node 2 is displaced by U2. So here is the displacement is a primary field variable, my dear students. The parameter which varies immediately with the application of the load in the domain, with the application of the load in the domain, that parameter is called primary field variable or nodal field variable. Or nodal field variable. All of you clear, my dear students? Now, in this case, suppose if the problem is a structural problem, if the problem is structural problem, the nodal field variable is displacement here. All of you see, it is a very important. So here is it is a structural problem, because due to this load there is due to this force P1 at node 1, P2 at node 2, this node 1 is displaced. So that if the problem is a structural problem, the nodal field variable is displacement. Next one. If the problem is heat transfer problem, if the problem is heat transfer, the nodal field variable is what is that? Temperature, my dear students. Temperature. Suppose if the problem is a fluid mechanics problem, if the problem is fluid mechanics problem, the nodal field variable is the velocity of the fluid. All of you clear, my dear students? Here is a temperature, here is a velocity of the fluid in case of fluid mechanics problem. In case of heat transfer problem, the primary field variable is temperature, my dear students. All of you clear? Next one, coming to secondary field variable. It is also called as element solution. So, all of you see, my dear students. So, in our case, we are finding the displacement at nodal points. By using that displacement, we are able to estimate strain. Strain is equals to change in length divided by original length. So here is a change in displacement divided by original length of the member. That is change in displacement divided by original length of the bar element. Original length of the element. Now here is, what is the change in displacement? U2 minus U1 divided by L. Yes or no? Now strain is represented by the letter epsilon. So that now here is a strain is a secondary field variable. By using strain, we are able to find stress. Stress is equal to Young's modulus into strain. So it is stress also secondary field variable. So strain, energy also secondary field variable. That is the parameter which can be determined by using primary field variables. That parameters are called as secondary field variables. Yes or no, my dear students? It is a strain, it is a secondary field variable. Okay, stress also secondary field variable. All of it clear, my dear students? So see here, the parameters which can be determined by using primary field variables. That parameters are called secondary field variables, my dear students. Secondary field variables. That is also called as element solutions. So what are the examples, my dear students? Stress, strain, strain energy, etc. Okay, all of it clear, my dear students? So the next one is nodal field variable vector. Nodal field variable vector. All of you carefully observe, my dear students. Suppose it is a structure. This can be divided into n number of pieces, my dear students. N number of pieces. Now it is a node 1, it is a node 2, it is a node 3, it is a node 4, it is a node 5. I will use different color for your clarity purpose, my dear students. Now this is element 1, this is element 2, this is element 3, this is element 4, my dear students. At element 1, for element 1, at node 1 displacement is u1, at node 2 displacement is u2, this is node 3 displacement is u3, node 4 displacement is u4, node 5 displacement is u5, my dear students. Okay. So the field variables at nodal points, it is a nodal point, it is a nodal point, it is a nodal. The field variables at nodal points. What are the field variables at nodal points, my dear students? u1, u2, u3, u4, u5. u1, u2, u3, u4, u5. The field variables at nodal points are represented in vector form. That vector is called as nodal field variable vector, my dear students. All of it clear? Okay. So here is a field variable. At node 1 field variable is u1. At node 2 field variable is u2. At node 3 field variable is u3. So all the field variables at nodal points are represented in vector form, my dear students. That vector is called as nodal field variable vector. I will write here. The field variables at nodal points are represented in vector form. That vector is called nodal field variable vector. Nodal field variable vector, my dear students. Next, coming to load vector. What is a load vector? See, again, consider it is a domain. It is a domain, my dear students. This domain is divided into small pieces like this, like this, like this. So now it is a node 1, it is a node 2, it is a node 3, it is a node 4, because joining of these two elements, here is a node, yeah. So here is a node 5, here is a node 6. Okay. So I will use a different color for your clarity purpose, my dear students. At node 1, load acting is P1. At node 2, load acting is P2. At node 3, load acting is P3. At node 4, load acting is P4. At node 5, load acting is P5. At node 6, load acting is P6. The loads acting at nodal points are represented in vector form. That vector is called as load vector, my dear students. The loads acting at nodal points, see, my dear students, it is a load vector. The loads acting at nodal points, that is P1, P2, P3, P4, P5, P6. So the loads acting at nodal points are represented in vector form. That is called as a load vector, my dear students. Whatever the loads acting at nodal points, that are represented in vector form, that is called as a load vector, my dear students. This is a load vector. All of it clear? I will write here, don't worry. The loads acting at nodal points are represented in vector form that vector is called load vector. All of you clear, my dear students? Okay, next coming to what is a stiffness? Consider, all of you see, my dear students, it is a bar. It is a bar, my dear students. One end is fixed, other end is free. Now I am applying load this end, free end, by P load. For suppose the length of the bar is equals to original length of the bar is L. Because of the load, there is a deformation in the bar. So for producing 1 unit deformation, my dear students, for 1 unit deformation. So for 1 unit deformation, my dear students, whatever load is required, how much load required to produce 1 unit deformation, that is called as a stiffness. For 1 unit deformation, whatever load is required. Okay, so that is called as a stiffness. Load required to produce 1 unit deformation. For making 1 unit deformation, how much P is required? Suppose this is a delta L. For making delta L 1 unit, 1 unit is nothing but either 1 meter or 1 centimeter or whatever it may be, 1 mm, whatever it may be. For making 1 unit deformation, how much load required? That is called as stiffness. Yes or no, my dear students? So load required to produce 1 unit deformation, that is called stiffness. That is called stiffness, my dear students. So mathematically, stiffness is represented by the letter K. K is equal to load required to produce 1 unit deformation or 1 unit deflection, my dear students. But we know, according to strength of material, what is delta L? PL by AE, my dear students. PL by AE. Substitute that value here. PL by AE. This P cancel out. That is equals to K is equals to AE by L, my dear students. All of it clear? So now the stiffness is a function of area of the element. It is a geometry. It is a Young's modulus. It is a material property. So the stiffness, it is a function of geometry and material, my dear students. So stiffness is a function of geometry and material. All of it clear? Now this stiffness, consider, suppose it is a domain. I am dividing this domain into small pieces. So the stiffnesses at nodal points. So here is a stiffness, this is node 1, here it is node 2, here it is node 3, here it is node 4, here is node 5. Now this is element 1, this is element 2, this is element 3, this is element 4, my dear students. So elements are represented with a circle, my dear students, number with circle. Nodes are represented only numbers. Okay. So the stiffness values at nodal points. So what is the stiffness at node 1? What is the stiffness at node 2? What is the stiffness at node 3? What is the stiffness at node 4? What is the stiffness at node 5? The stiffness values at nodal points are represented in vector form, matrix form. The stiffness values at nodal points are represented in matrix form. That is called as a stiffness matrix, my dear students. The stiffness values at nodal points are represented in matrix form. That matrix is called stiffness matrix. Okay. This stiffness matrix is a square matrix, 2 by 2, 4 by 4, 3 by 3, like that. So stiffness matrix is a square matrix. So it is also, stiffness matrix also, it is a symmetric matrix. All of you clear, my dear students? So these are the different terms used in finite element methods, my dear students. All of you clear? Next here, we know that what is the stiffness? Stiffness is equals to P by delta L, that is equals to P by delta L is nothing but PL by AE. This one cancel out. So that is equal to stiffness K is equal to AE by L, my dear students. But what about our main equation? K is equals to P by delta L. Now this can be for nodal, that is stiffness values at nodal points are represented in matrix form. This is the stiffness matrix. So here is a delta L is nothing but it is a nodal field variable vector, that is field variables at nodal points are represented in vector form, that is nodal field variable vector, that is equal to P. It is a load vector, that is loads acting at nodal points that are represented in vector form. This is a load vector. This equation is called as equilibrium equation. This equation is called equilibrium equation, my dear students. This is equilibrium equation, my dear students. So for case of delta L, this is a deformation that are represented, that is displacement, that is field variables at nodal points that are displacements represented in vector form. That is a nodal field variable vector. So the loads acting at nodal points are represented in vector form. That is a load vector. All of you clear, my dear students. Thank you.